गुड मॉर्निंग बच्चों। आज हम हाइड्रोजन बॉन्डिंग के बारे में डिस्कस करेंगे। जैसा कि हमने यहाँ लिखा हुआ है कि कोवेलेंट बॉन्ड इज स्ट्रॉन्गर देन हाइड्रोजन बॉन्ड इज स्ट्रॉन्गर देन वान डेर वाल्स फोर्सेस। यानी हाइड्रोजन बॉन्ड जो है बेसिकली इट इज़ नॉट ए बॉन्ड, इट इज़ ए वी कैन से स्ट्रॉन्गर फोर्स देन दैट ऑफ द वान डेर वाल्स फोर्सेस. Okay, so it is nothing but a intermolecular force of attraction which is stronger than van der Waals forces, but it is quite weaker as compared to the normal bond which is a covalent bond or a ionic bond. So hydrogen bond, though it is weaker than covalent bond, but it is quite stronger as compared to the van der Waals forces. Now let us take one example. Suppose this hydrogen, let us take hydrofluoric acid HF. Now you see this hydrogen is bonded by a covalent bond, single bond with fluorine, and fluorine is highly electronegative as compared to hydrogen. If we see the electronegativity on the Pauling scale, then the fluorine has around 4.0, then oxygen has around 3.5, nitrogen has around 3.0. So these are the most electronegative elements. Okay, so whenever hydrogen is attached with either of these three, either fluorine, oxygen or nitrogen, which you can remember by form, okay, then this shows hydrogen bonding. Now how hydrogen bond is formed? Because the fluorine is highly electronegative, it pulls the shared pair of electron towards itself. So it will get some delta minus, that is partial negative charge, and this hydrogen will get partial positive charge. Okay, now this hydrogen seeks the electrons. So the surrounding molecule of this HF, this F has lone pair of electrons. Okay, because fluorine, what is the electronic configuration? 2,7. So one electron is shared with the hydrogen, and it has 3 lone pairs of electrons. So this hydrogen will form a bond with this fluorine. Okay, and this bond is known as hydrogen bond. So if I ask you, suppose you are given hydrogen, hydroiodic acid Hi, then HBr, HCl and HF. So what will be the order of boiling points? Okay, normally we know that van der Waals forces increase as the molar mass increases. So hydrogen iodide, that is Hi, has the highest molar mass and HF has the lowest molar mass. So the normal order of boiling points should be Hi greater than HBr is greater than HCl is greater than HF. That should be the normal order of boiling points. But it was found that hydrofluoric acid has the highest boiling point. So the order will be HF greater than Hi greater than HCl, HBr and greater than HCl. HF has the highest boiling point. This is because of the hydrogen bonding present in HF molecules. So this is an intermolecular force of attraction that increases because of the hydrogen bonding. Okay, now let us take some other examples. Why alcohols have higher boiling points than ethers? Okay, as we know, alcohols are ROH. So hydrogen is attached with electronegative element, that is oxygen, So it will have delta minus and hydrogen will have delta plus. And one more molecule, if I take say ROH, now this has the lone pair of electrons, so this hydrogen will make hydrogen bond with this oxygen shown by this dotted line. So this, due to this intermolecular hydrogen bonding, this alcohols will have higher boiling points. But in case of ether, which is RO R prime, there is no hydrogen atom attached directly with the electronegative oxygen atom, so it will not show, there will be no hydrogen bonding in ethers. That is why ethers have a lower boiling point as compared to alcohols, and alcohols have higher boiling point. Now let us take one more example. Why glycol and glycerol have higher boiling points than even water and your alcohols, other alcohols. Okay, we know what is glycol. Glycol is CH2OH single bond CH2OH, and the boiling point of glycol is around 197 degrees Celsius, which is higher than water having around 100 degrees Celsius, and alcohols around 72 degrees Celsius, say ethanol. Now why this has higher boiling point? The reason is it has two OH groups. Okay, so it will show extensive hydrogen bonding because of this delta plus, and this will have delta minus, and this CH2OH, this is having delta plus, this is having delta minus, and the surrounding molecule of this glycol will make hydrogen bond with this other molecule. So there will be very extensive hydrogen bonding in the glycol. If we take glycerol, glycerol is CH2OH single bond CHOH single bond CH2. It is a trihydric alcohol. There are three OH groups, so the hydrogen bonding extent will be even higher than that of glycerol, and it has a still higher boiling point around 290 degrees Celsius. And we know that glycerol is highly viscous, though this ethylene glycol is also highly viscous, but glycerol is even more viscous than this glycol. The reason is again more extensive hydrogen bonding because of the three OH groups present in the glycerol. Okay, so these are the few examples. This water has also very extensive hydrogen bonding. How we will show here? Suppose this is our HOH molecule. Now this is having delta minus, this H is has delta plus, this also has delta plus. Suppose there is another molecule HOH, then this hydrogen will make, this is delta plus, this is delta minus, this will make this hydrogen bond with this oxygen, and similarly this oxygen, because it has two lone pairs, so it can make another hydrogen bond with a surrounding molecule here. See, this is delta plus, this is delta minus, and this will make hydrogen bond with this oxygen. Okay, so we can say that each molecule of water is making how many bonds? 4 bonds. How? Because let us take this water molecule. One is this hydrogen bond, one is this, and there will be another with this. Okay, so this will make another hydrogen bond with this, and this hydrogen will make another hydrogen bond with a oxygen atom. Say here one oxygen, so this will make hydrogen bond. So we can say that each molecule of water is making 4 hydrogen bonds. Okay, so this, let us take this molecule. How many bonds it is making? 1, 2, 3, 4. So each molecule of water is making 4 hydrogen bonds. So we can say it is very high extensive hydrogen bonding in water, and this is the reason why in the 16th group elements, halides, these hydrides, that is H2O, and we have H2S, we have H2Se, we have H2Te. So what is the order of boiling points? The normal order of boiling points should be H2Te greater than H2Se, greater than H2S, greater than H2O. Because we know that van der Waals forces increase with the increase in molar mass. H2STE has the highest molar mass and this has the minimum molar mass. So this has higher boiling point, but due to extensive hydrogen bonding in water, the order of boiling points is H2O greater than H2T greater than H2Se greater than H2S. So that is the actual order. So we can say that hydrogen bonding has a great role in determining the physical properties of compounds like boiling points, viscosity, etc. Okay, now let us take one example, that is for intramolecular hydrogen. We know that there are two types of hydrogen bonding. One is intramolecular and other is intermolecular. Okay, so let us take two examples which will show a single compound shows intermolecular as well as intramolecular hydrogen bonding. That is two isomers of a organic compound. Okay, let us take para nitrophenol and ortho nitrophenol. Okay, so what is ortho nitrophenol? This will be like this. This is phenol and ortho position is this. So here we'll have N double bond O, single bond O, and this I can write as O single bond H. Okay, now this O will have delta minus, this hydrogen will have delta plus, and the lone pair of oxygen is there. Okay, so this lone pair will make hydrogen bond with this oxygen. So this is called intramolecular hydrogen bonding because it is within the molecule. Okay, now this is ortho nitrophenol. If I take para nitrophenol, then what will happen? This will have intermolecular hydrogen bonding and not the intramolecular. So suppose this is OH and this is N double bond O, single bond O. So this is NO2 group and this is the OH group. Okay. Now I will make one more molecule here. Like this, and this is the O single bond H, and this will be N double bond O single bond. So this is NO2 attached at the para position. So now we see they will make intermolecular hydrogen bonding. This is having delta minus oxygen, this is delta plus, and oxygen has the lone pair, so this hydrogen will make intermolecular hydrogen bond with this oxygen. So we can say that this para nitrophenol is showing the intermolecular hydrogen bonding with the surrounding molecule. And as we know that the boiling points will increase when there is a intermolecular hydrogen bonding, because intramolecular hydrogen bonding does not affect the boiling point, because this hydrogen bonding is within the molecule and intermolecular is between the two molecules. So boiling points will be affected only by the intermolecular hydrogen bonding. So we can say that para nitrophenol has higher boiling point as compared to orthonitrophenol. Okay, so this is the example of intramolecular and intermolecular hydrogen bonding. We can also say that orthonitrophenol is more volatile, is more volatile as compared to para-nitrophenol, which has a higher boiling point. And we can say that both these can be separated by fractional distillation, because there is a difference in their boiling points. Now let us take some examples of this which affect the solubility. Okay, sometimes the molecules are soluble, these two compounds are soluble in each other because of the hydrogen bonding. Now let us see this example of, say, alcohols are soluble in water because of hydrogen bonding, that ROH will have with HOH, because this will have delta minus, this is delta plus, and this oxygen lone pair, so they will make hydrogen bond with ROH. So we can say that alcohols are soluble in water, and those compounds which do not make hydrogen bonding with water, they are not soluble in water. Okay, there may be many examples like alkanes are not soluble in water, alkenes are not soluble in water because they do not form any hydrogen bonding. Similarly, we can say that amines are soluble in water. Amines are soluble in water. Why? Because what is amine? RNH2. Okay, and this is our water, say HOH. Now this is N is delta minus, this H is delta plus. Okay, now this oxygen lone pair, so this hydrogen will make lone pair with this water. So amines are soluble in water because they form hydrogen bonding with the water. Okay. Similarly, ammonia is highly soluble in water because ammonia also makes hydrogen bonding with water. Now we see this S3BO3. This is a molecule called boric acid. This exists as S3BO3 2. Why? This is because of hydrogen bonding, that is intermolecular hydrogen bonding. We can represent this as BOH, BOH, OH. So this is your H3BO3. Now we see this will show hydrogen bonding. Okay. If we want to see this, how it shows the hydrogen bonding, we will rewrite it as like this: BOH, OH, OH, and another we will write B, like this. Now we see this is delta minus, this is delta plus, this is delta minus, this is delta plus. So this will make hydrogen bond with this, and this hydrogen will make hydrogen bond with this oxygen having lone pair. This oxygen is also having lone pair. So that is how it is a ring type structure is maintained. This is called chelation, that is formation of a ring due to hydrogen bonding. So S3BO3 exists as S3BO3 twice. That is a dimer of boric acid. And similar is the case with carboxylic acids, which also exists as dimer in when present in benzene. So RCOOH, that is your carboxylic acid. They also form intermolecular hydrogen bonding and form a ring type structure. That is why they will exist as RCOOH twice in benzene. So that is again due to the hydrogen bonding. So with this we complete our discussion on hydrogen bonding. Okay, I wish you all the best. Thank you.